Hello, in this lecture we're going to start studying automata. This picture contains most of the topics that we're going to see in this class. So let's take a look at it. We're going to start with the regular languages covering automata, non-deterministic automata, regular expressions. Then we're going to move on to context-free languages, where we're going to see context-free grammars, push-down automatas. Then we're going to move to decidable languages. We're going to see Turing machines. And finally, we're going to come back in the middle and study complexity theory, and specifically the classes P and NP. This picture is in order of generality. So following this arrow, you go to more and more powerful models. Okay, the most restricted model is that of regular languages, and the most general one is all languages. Okay, and context-free is more powerful than regular. P is more powerful than context-free. It is not known if NP is more powerful than P. That's the P versus NP question. It is known that decidable languages are more powerful than NP, and all languages, as we're going to prove, are more powerful than decidable. Okay. After this overview, let's start with automata. So the best way to start with automata is via a picture. So here's a picture. This is a picture of what we're going to call a DFA. So this stands for deterministic, because later in this class we're also going to see non-deterministic finite automata. F stands for finite, because there is a version of these things which is infinite. It has an infinite number of states. However, we are not going to study that in this class. And automata is an ancient name for computer. Just think of it as computer. Okay, and here is a picture of how they look like. So here are the main features of this picture. So this DFA will have states, okay, which are just written as a circle. This particular DFA has 4 states. Okay, so this is a state, this is a state, this is a state, this is a state. And it has transitions or edges. So transitions are just arrows with a direction. And these transitions are labeled with elements from the alphabet, the input alphabet, which here is 0, 1, is the alphabet 0, 1. And we usually denote alphabets with the capital sigma letter. Okay, so fine. How does this thing compute? So here is how this thing computes on a given input W. We're going to begin the computation in the start state. Okay, the start state is the one which has an arrow that goes into it, but does not come from anything. Okay, so here it's Q0. Then we're going to read the input string in a one-way fashion. And you're going to follow the arrows matching the input symbols. When the input ends, if you are in an accept state, you're going to accept. The accept states are the ones with a double circle. And if you're not in an accept state, you're going to reject. So this computer only computes 0, 1, yes, no, true, false functions. Okay. All right, let's do an example. Here is an example of a DFA. And let's say that the input string W is 0, 0, 1, 1. Okay. So what do? We start the computation in the start state. Okay. And then we're going to read the first symbol of W, and we're going to follow the corresponding transition that moves us to another state. We're going to continue doing that, read another 0, then read a 1, then read a 1, and now the input is over. There is nothing else to read, and we're going to accept because we ended up in an accept state. Let's do another example. Let's consider the input string at 0, 1, 0. We always start in a start state. We read a 0, we follow the corresponding arrow. We read a 1, and then we read a 0, and then the input is done, and we reject because we did not end up in an accept state. Here is other examples. 0, 1 is accepted, 0, 1, 0 is rejected, 0, 0, 1, 1 is accepted, and 0, 0, 1, 1, 0 is rejected. For example, let's consider 0, 0, 1, 0. Okay, we start in the state here, we read a 0, then we're going to read another 0, we're going to follow this self loop here, we read a 1, we go to a start state, an accept state, but we don't end there, because then we're going to read another 1, we do another self loop, and then the final symbol is a 0, we get out of the accept state, input is over, we are not in an accept state, you reject. So we're going to denote this DFA by M. Okay, so M is this DFA. And what strings are accepted by M? We're going to say that M recognizes the language L of M. L of M is the language of strings that cause M to accept. Okay, LOM is a set of strings, are the strings that cause M to accept. So if you think about it, what strings are accepted by M are those that start with a 0. Okay, you gotta start with a 0 because if you start with a 1, you immediately go here and you will not be accepting. Okay. And then the strings have to end with a 1. Okay. If you end with a 0, you will be in this state here. But if you end with a 1, you will end up here in this accept state here. To make clear this notation, we can say that the 0, 1, 0, 1 is an element of L of M. Okay, it's a string which belongs, this is the symbol for belong, to the set L of M. Great. Let's see other examples. Again, we have the alphabet 0, 1. Here is another M. So we see this, that 0, 0 causes M to accept. Right? We start in Q0. If you follow 2 zeros, we end up here. So 0, 0 is an element of L of M. On the other hand, 0, 1 does not cause M to accept. So 0, 1 is not in L of M. 0, 1 is not an element of L of M. Other examples, 0, 1, 0, 1 is in L of M. 0, 1, 1, 0, 1, 1, 0, 0 is in L of M. 0, 1, 1, 0, 1, 0 is not in L of M. So we can ask now, what kinds of strings cause this DFA to accept? And if you think about it, the language of M are the strings which have an even number of ones. Okay? If you have an even number of ones, you're going to end up in the if you have an even number of ones, you're going to maybe do back and forth, but you're going to end up in Q0, which is an accept state. If you have an odd number of ones, you may do some back and forth, but then you end up in Q1, which is not an accept state. And note an important convention that if there is no 1, so you have 0 ones, so 0 we consider it to be an even number, okay? 0 is an even number, so M should accept. And indeed, this is what happens in this case, because, for example, the string consisting of these many zeros is in the language M. Okay, let's see another example. Here is another DFA. What is the language of this DFA? So I'm going to have several points in these videos in which I have question marks, okay? And I'm going to ask questions, and you should now pause now and think about the answer, and then see if it's correct. So you can pause the video when you see the question mark. Done? Okay, good. So let's see. It accepts every string, right? It accepts every string, every possible string over 0, 1, which we denote by the set 0, 1 star. This is the so-called clean star. And this means every string over the alphabet 0, 1. Okay. Let's see another example. What does this DFA accept? Again, a question mark, so you can pause the video here and think about it. Well, let's see. We start here. If we do 0, we go here where we always accept. If we do 1, we go here where we always accept. So the language of M is the set of all strings except the empty string. So a possibility for the input is that you give me nothing, epsilon. So epsilon seems weird, why are we even bothering with this? Well, we bother with epsilon because we bother with 0, okay? It was a major revolution in science to have zeros, like the ancient Romans didn't have it, okay? And they had all these complicated numerals, and then other cultures, they came up with this idea of zeros, and it's been a major simplification of everything. And it turns out to be also a major simplification of theory of computation if you allow for the empty string. Okay, so the empty string is denoted by epsilon, Greek letter epsilon, and this automata accepts every string except the empty string. Okay, so 0, 1 star minus the set containing just epsilon. And here's another example. What does this accept? Try to guess. This accepts the strings which start and end with the same symbol, right? Because if I start at Q0, if I read a 0, I go here, then the only way that I'm going to accept is whether I end up after reading some bunch of zeros and ones. I need to end up here, and I only get here if I read zeros. Okay, and I stay here. If I read a 1, if I end my input with a 1, I will be in this state here, and that's not an accept. Similarly, if you read a 1, you go here, and you're only going to accept if you're going to end the input with a 1. So this example is extremely important. Somehow this DFA is remembering, so it has some memory. But hold on a second. We said that it has no memory. Well, it has a constant amount of memory. Okay, constant amount of memory. And where is the memory encoded here? Think about it. Where is the memory? The memory is in the states, right? So you should think of states as the memory of the machine. So if you are in these two states here, you remember a 0. If you are in these two states here, you're going to remember a 1. So DFA have a finite number of states. Okay, that's the F in DFA is finite. So they have a finite amount of memory. Okay, now the pictures are going to get pretty complicated, so we're going to have some conventions to simplify the pictures. Here is a DFA, and we already saw that the language of this DFA is a set of strings which start with 0 and end with 1. Okay, so this arrow here leads to a so-called sync state. Okay. If you follow that arrow, M can never accept. Okay? So you know what? Let's not even draw it. Okay? So we are not going to write such arrows, okay? We're going to adopt the convention that if you are in some state Q0 and you read a symbol from the input which has no corresponding arrow, then you can imagine that M goes into a sync state that is not shown, and you eventually reject. Okay? This is going to make pictures more compact. We're going to have other conventions. We're going to list multiple transitions on the same arrow. So for example, if you have an alphabet sigma of 0, 1, and 2, okay, I can write one arrow with label 0, 1, 2, which means you follow this transition if you read a 0 or a 1 or a 2. And this just corresponds to having 3 arrows, one for each symbol. And again, this is going to make pictures more compact. So here's an example now over the alphabet 0, 1 is M. What does this DFA recognize? It recognizes all the strings of length 2. All the strings of length 2. These are the strings of length 2. And we can write that as sigma square. Okay? Sigma square are the strings of length 2. And more generally, sigma to the k for some number k are the strings of length k. Okay. So again, here I use both conventions. I have 2 labels on one arrow, and from my accept state, I did not put any arrow, which means that if you read anything from the accept state, it would be just going to a sync state. All right, here is a more interesting example of DFA. Here is an example from programming languages. Okay, as we mentioned earlier in the introduction, we have to recognize well-formed numerals and variable names. Okay, so in particular, we're going to recognize numbers. So we want, we want to be able to recognize things like, minus 0.5, okay, but not things which are not well-formed. Okay, so this is such a DFA, and it can very well be a DFA that's used in a modern programming language. Okay, and remember that we use the convention that we can write multiple labels on one arrow. So I'm going to write here 0.9 to mean that you have any of the 10 transitions corresponding to the digits. Okay. So how does this thing work? Well, here's how it works. You start the start state, and then you can possibly put a sign. You can possibly put a plus or a minus, and that has to be followed by arbitrarily many digits, but at least one. Okay, I cannot just end my input after one sign. I would end up here. That's not good. Okay. So you have to follow with arbitrarily many digits, but at least one. Okay. So this transition here guarantees that you have at least one digit after the sign. Then you can have as many digits as you want. You will cycle here. And then you may want to put the decimal point at some point. Okay, you put this decimal point just once. And then again, you follow with arbitrarily many digits. And here we allow for possibly no digit. You can write like +5 dot. That would be accepted here. Okay, so observe, you can put a sign, you can put a decimal digit, but only once. Okay, after you put it once, you're not allowed to do it again. In particular, if you are in the state here and you read one more dot, you should think again that you go to a sync state. Okay, so for example, on the input 17, you don't accept the input plus. Okay, you accept minus 3.25. You will not accept plus 2.35 minus dot. Let's do another example. Let's think again about the alphabet 0, 1. What about this language here, the language of strings which have the same number of zeros and ones? Can you design a DFA that recognizes that? Well, it seems that you will need infinite memory for that. And indeed, we're going to prove later that there is no DFA that recognizes that language. Right? Here is an example of something which is impossible by DFAs. Okay, and impossibility results are really, are an extremely important aspect of theory of computation. Okay, what will come next is a formal definition of DFA to make things precise. And this thing is now so important for showing DFAs. You can just show the DFA in it and it's clear, but it's especially important if you want to prove that things cannot be recognized by DFA. Okay, so again, if I want to show you a DFA, I can draw a picture. That might be enough. But if I want to show to you, if I want to prove to you that something cannot be recognized by DFA, there is no DFA for that, then I want to be really, really precise on what I mean by DFA. Okay? Because how am I going to convey that with a picture? You can't. Okay? Then you need a formal definition, and that's what we're going to do next. And it's also useful for us as a mathematical playground to practice mathematical notation.